In this video, we'll discuss about the core intuition behind artificial neural networks. We'll see why traditional machine learning models are not enough and why do we need these hidden layers. So, artificial neural network or ANN actually mimics our biological brain. So, in ANN we have lots of nodes or neurons and weights associated with those. In biological brain, we have lots of biological neuron or nerve cells. Those are connected to each other. So, if you see, one artificial neuron also mimics a biological neuron or nerve cells. So, this is one biological neuron. We have the cell body here and inside that we have the nucleus where some operation happens. These are the dendrites which receives signals. Then after some operations, via this axon, the signal passes and these are the synapses. This outputs the signals. In artificial neuron, so let's consider our traditional ML models like linear regression or logistic regression, right? So there we had one single model or single node. We were taking inputs and then we are performing some linear calculations. We are also applying activation functions if needed, and then after that we are returning the output. So the biological neuron and the artificial neuron are quite similar. So basically this artificial neuron are inspired by this biological neuron. So if you see the biological neural network, so these are the biological neurons. Those are connected to each other. Consider these neurons, it is receiving signals using its dendrites, doing something and then passing the signal to the next neuron. This also receives the signal, doing some operations and passing the signals to the next neural network. So the same idea applies to our artificial neural network, where we stack neurons layer by layer. So first we'll see why traditional ML models are not enough. So in our traditional ML models like linear regression, logistic regression, SVM, decision trees and all, this works well only for limited problems. So as data and problem complexity grows, they start to fail. Poor performance on unstructured data. So this traditional ML models are not good for unstructured data like images, audio, text, video, etc. Also, these are not well with big data. So these are few shortcomings for traditional ML models. So for complex problems and to deal with big data, we need something better. Next, why we need hidden layers? So to learn complex non-linear patterns and create hierarchical feature representations, complex problems can't be solved without hidden layers. And most real-world problems are impossible to solve with only input and output layers. So we'll see with examples. So let's think about logical AND operation. We are taking two inputs A and B, and inputs can be 0, 0, 0, 1, 1, 0 and 1, 1. These four possibilities. Only when both the inputs are 1, then only it will output 1. So in this case, blue is for 1, red is for 0. For 0, 0, 0, 1 and 1, 0, the output is 0. So you see the decision boundary here, this is linearly separable. In this side we have zeros, in this side we have 1. Consider the logical OR operation. So only when both of the inputs are 0, then only the output will be 0. In all the other cases, output is 1. Only for 0, 0, the output is 0, and for all the other cases, output is 1. So this decision boundary is also linearly separable. This side we have 0, this side we have all 1s. Similarly, if we consider NAND or NOR, so it will be just opposite. For NOR, this side will have 1 and for all this it will be 0. Consider XOR operation. For 0, 0 it outputs 0, for 0 1 and 1 0 it outputs 1, and for 1 1 again it outputs 0, right? So you see, for 0 0 it is 0, for 0 1 it is 1, for 1 0 it is 1, but for 1 1 again it is 0. So the decision boundary is not linearly separable here. You cannot draw a line and separate these points, right? If you draw a line like this, here also you have 0, here also you have 0. In both the side you have 0. You cannot draw a line in any possible way to distinguish this. So XOR function is basically not linearly separable. Now we saw earlier that AND, OR, NAND, NOR, all these operations, these are linearly separable. The decision boundary is linearly separable. So we'll see if we can represent it with one node or neuron. X1, X2, these are inputs. So we can have these four possibilities: 0, 0, 0, 1, 1, 0 and 1, 1. So we are doing some calculation in this node or neuron, right? So let's say these are weights assigned here. So if you take a linear combination of the inputs, it will be like W1 X1 plus W2 X2. This weights are something that will get trained when we will train the model, right? So this can be any continuous value, but our output we want is either 0 or 1. So that's why we are taking one sigmoid. We are applying sigmoid on this. So here I have represented the equation here. So also I have taken one bias B1. So when we'll train the model, we'll get to know the values of W1 and W2. But let's say we know the values. I have one values here that satisfies our equation. So sigmoid of this thing 20x1 plus 20x2 minus 30. So let's see, when both x1 x2 is 0, we get sigmoid of minus 30. So that is 0. When x1 or when one of this is 1 and one of this is 0, we get 20 minus 30, that is minus 10. So in both of these cases we get sigmoid of minus 10, which is also 0. When both are 1, we get 20 plus 20 minus 30, that is sigmoid of 10, which is 1. So only when both input are 1, so then we are outputting 1. So this acts like a AND model. So we can represent AND with a single neuron or node. Now let's check for the OR operation, logical OR operation. So we have come up with a similar equation, x1, x2 is input, and we have come up with this equation. And also let's say we know the weights. We got sigmoid of this thing 20x1 plus 20x2 minus 10. So when x1, x2 both are 0, we get sigmoid of minus 10, which is 0. When x1 0, x2 1 or x1 1, x2 0, means one of them is 0, one of them is 1. In this case, we get sigmoid of 20 minus 10, that is sigmoid of 10 in both the cases, and we get 1. When both are 1, right, we get sigmoid of 20 plus 20 minus 10, that is sigmoid of 30, which is also 1. So only when x1 and x2 both are 0, then we are getting output as 0, otherwise 1. So this actually works like a OR model. So with a single model, with a single node or neuron, we are able to represent OR function model. But now let's see about the XOR function. So the decision boundary is not linearly separable here. So we cannot draw a line to separate zeros and ones, right? So here you see, if you draw this line, here in this side also you have 0, in this side also you have 0. So with just one neuron, you won't be able to solve XOR function. But let's see how we can represent XOR mathematically. So this is one representation of XOR. x1 XOR x2 can be represented as x1 or x2, and this is AND x1 and in x2, and then we are applying the NOT here, so this actually becomes NAND, and then we are taking the AND operation here. So let's see if this works. So I have taken 4 types of inputs: 0 0, 0 1, 1 0, 1 1, and let's see, let's calculate the values. this is 0, this is 1, this is 1, this is 1. Now these are actually effectively calculating in NAND, so this will be 1, this will be 1, this will be 1, this will be 0. Now let's take the AND of these values. We get 0, 1, 1, 0. So this acts like a XOR operation. So this is one representation of XOR. There can be other representations as well, like this is another representation of XOR, like x1 XOR x2 is x1 and not x2, and here we have not x1 and x2, and we are taking the OR of these two. So now my point here is to come up with a XOR function. We first had to calculate this and this, and the result of this two. For this result of this two, we have to apply the AND, a separate operation. So this actually hints that we need some intermediate layers to calculate this values first. Then we'll be applying a second operation. Now let's see if we can represent XOR with hidden layers. So now let's say we have added one hidden layer with two neurons, H1 and H2, and these are the inputs and these are weights assigned in the first layer, these are weights assigned in the second layer. So these weights will get trained when we actually train the model, but here let's say we already know the answers, we already know this weight values. So let's say in H1 I have taken the OR function, in H2 I have taken the AND function. So you already have seen the OR function, that is sigmoid of this 20x1 plus 20x2 minus 10. For AND we had sigmoid of 20x1 plus 20x2 minus 30. And now we are calculating the Y, the actual output, as a function of H1 and H2. So let's say I have taken sigmoid of this 20H1 minus 20H2 minus 10. So I am saying this will work like a XOR operation. So let's see how it works. So here we have four scenarios: 0, 0, 0, 1, 1, 0, 1, 1. Right? So in H1s we are calculating the ORs, H2 we are calculating the ANDs. So let's first do this calculation. So 0, 0 OR we are getting 0 here, 0, 1 we get 1 here, 1, 0 we get 1 here, 1, 1 we get 1 here. For ANDs we get 0, 0 we get 0 here, for 0, 1 we get 0 here, for 1, 0 we get 0 here, for 1, 1 we get 1 here. Now we found the values for the hidden layers. Now we have to calculate the actual output. So what is this? 20H1 minus 20H2 minus 10. This we have to apply, right? So when both H1 and H2 are 0, we get 0 sigmoid of minus 10, that is 0. When H1 is 1, H2 is 0. In both these cases, H1 is 1, H2 is 0. We get 20 minus 10, that means sigmoid of 10, which is 1 in those two scenarios. And when both H1 and H2 are 1, then we get 20 minus 20 minus 10, that means sigmoid of minus 10, which is 0. So this actually works like a XOR model. So without these hidden layers, we won't be able to solve a function like XOR. So this is the intuition behind why we need hidden layers. So there will be much more complex networks we'll see going forward, where we'll need multiple such hidden layers. Now quickly I will just show one simple neural network and the notations I'll be using for the upcoming videos in this series. So here we have the input layers, we have the input nodes. These are the weights, and this is the nodes in the hidden layer, first hidden layer, let's say. So this superscript 1, it represents, this is the first hidden layer. This weights here, this also has superscript 1, so that is for the first hidden layer. This represents, these are the weights for the first hidden layers. W11 is basically from 1 to 1. this is from x2 to z1, so this is w21 for the first layer. These weights are representing second layer weights. What are these A1s? So this A1, A2, A3 for the first layer, these are the activation layers. So in this Z1s, we'll do some linear calculations and then we'll apply this activation functions like sigmoid. So there are lots of other activation functions, but we need lots of different types of activation functions. So this can be seen as a couple, this linear nodes and the activation nodes. So whenever if we add one stack of hidden layers, so there also will have like Z1 2, A1 2, Z2 2, Z2 A2 2 and so on. So this notations I will be following going forward, and this is the output layer Z1, and this output layer, it just has one node here, and this also will have some activation functions and then we'll get the predicted output.